Section 5.3, general solution for 2 degree of freedom systems. This derivation can get very long, and before we spend a lot of time deriving it and then trying to show all the pieces at the end and how they fit together, I think it's much better to just give you the solution. We'll talk about the solution, and then we will derive the solution, and we'll get back to what we talked about, right? So you can start to kind of see it come out of the ether a little bit as we go, and you can understand what all the terms mean. So let's just hand out the solution. We have a 2 degree of freedom system problem, and this is the one that we are generally going to consider for a while in the class. We have a mass on our frictionless rollers. We have a second mass on our frictionless rollers. And then we have x1 and we have x2. Maybe it's best to call that mass 2, mass 1, and then stiffness 1 and stiffness 2. So that's our 2 degree of freedom problem. Now we need a solution, right? Again, our solutions are always in terms of our displacement x. Now it's going to be x1 as a function of t. And I just want to know how my mass 1 is going to move through time. And that is equal to a1, which will be my amplitude, times my sine of omega 1, which is my frequency or my natural frequency for the first mass, or just my frequency for the first mass, multiplied by t, which is the time step that I'm at, plus phi1. And all of that is in parentheses for the sine. And then this is multiplied by my modal element u, which we talked about, 1, 1. So for mass 1, mode 1, plus a2 sine of omega 2. So that's the natural frequency of my second mass, multiplied by my time, plus my phase of my second mass, all in closed parentheses, all multiplied by u1, 2. And so that's my modal element for mass 1 for my mode 2. x2 of t is going to be pretty much identical. I'm going to have amplitude of 1, sine of omega 1 t plus phi, phi1, close bracket. So everything up here, everything to that point is perfectly identical. But now I'm going to have my modal element 2 for mode 1 plus a2 sine of omega 2 t plus phi 2 u 2, 2. That's my modal element for u2, 2. Now there is one aspect where this does not work, and that is that omega 1 or omega 2 cannot equal to 0, right? So they both have to be moving, right? Otherwise it's not a vibration problem, right? It's just a 1 degree of freedom problem, and those solutions would suffice. Okay, so this is a really nice equation, but it's 2 equations. And when we start to work with multiple degrees of freedom, we want a way to write this more compactly. So we can put this into matrix notation, matrix vector notation, right? So I'm going to have x vector, that's a little arrow t, is equal to a1 sine of omega 1 t plus phi1 u vector of 1 plus a2 sine of omega 2 t plus phi 2 of a vector, so a little u with an arrow, t, and again, it's omega 1 or omega 2 is not equal to 0. Okay, so that brings us into a matrix notation for our system. Again, x vector of t, that's just x1 of t, x2 of t. U vector 1, that's my mode shape, which consists of my elements u11 and my elements u21. And then I've got my vector u of 2, an equal sign there, is u12 and u22. Okay, so we've got 4 key components here. We have omega 1 and omega 2, and those are the natural frequencies of the system. They are not the frequencies of the masses, right? Because they interact with both. The solution states that each mass oscillates at the summation of these 2 frequencies, right? So it's not one mass moving at omega 1 and one mass moving at omega 2. It's both masses moving at the frequencies of omega 1 and omega 2. And you can see that if you were to set like A1 equal to 0, well, we'll do that later. Let's not get off on a tangent there. Okay, and then there's also A1 and A2. And those are constants of integration, and they determine the amplitude of the system, right? You might have more energy at omega 1. You might have more energy at omega 2. That's what those do. Phi 1 and phi 2, that's going to give you any initial phase that's coming into the system with your initial conditions. And, those are exactly like the ones we had before. And then U1 and U2, those are our mode shapes, the first and second mode shapes, and that's what couples the system together. If you don't have the mode shapes, you don't have your system coupled. You can have 2 1 degree of freedom problems, but you have to have the mode shapes to couple your systems together. So that's the solution that we are working to. So now that we know where we're going to end, right, we're going to, so if you don't write much down, write this down. So now that we know where we're going to end, let's work our way there.